After creating pharmacophore sites on all conformers of all ligands, the next step in the developed pharmacophore workflow is to find common pharmacophores. In this step, we'll attempt to find arrangements of pharmacophore sites that are common to our active compounds. Keep in mind that we're not yet determining which commonly shared pharmacophore site arrangements best describe the features that confer activity. We'll do that later. Right now, we're mainly concerned with identifying these common arrangements of features. As you can imagine, there are a couple of considerations that can affect our ability to find these common arrangements. The most obvious consideration is conformational coverage. Our ligand conformer sets that we either created or imported at the beginning of the workflow need to contain reasonably close approximations of the bioactive ligand conformations. You also want to make sure that you have a reasonably sized, reasonably diverse active set. Again, this is something that needs to have been taken care of at the outset of the workflow. There are certain specific considerations that may vary on a case-by-case basis. For example, suppose you know from previous research that a particular feature, such as a hydrogen bond donor, is essential to activity. Obviously, you'd want to enforce the presence of such a feature in the common pharmacophores that you find. Phase contains tools to help enforce these kinds of provisions. If we take a quick look at some of the features in this panel, it's easy to see how we can implement these considerations during the Find Common Pharmacophores step. At the top of the interface, we see these options under Define Variant List. Then, at the bottom of the interface, we actually see this variant list. The variant list is a list of possible pharmacophore types that we might find when we run the Find Common Pharmacophores calculation, and changing the options at the top of the interface will affect what variants appear in the variant list. For example, with the default settings we have here, you can see that there are variants with names like AADHH, AADHR, and so on. These variant names refer to feature types and the frequency with which those features appear. Remember, each feature type can be denoted with single-letter shorthand, A for acceptor, R for aromatic rings, and so on and so forth. So an AADHH variant would encompass possible pharmacophores that contain 2 H-bond acceptors, 1 H-bond donor, and 2 hydrophobic sites. You'll want to be aware that the presence of a variant in the variant list doesn't necessarily mean that it will show up in the results. For the AADHH variant, it means that each of the active ligands we're aligning have enough acceptor, donor, and hydrophobic features individually to describe an AADHH pharmacophore, but it doesn't necessarily mean that there's an AADHH pharmacophore that's shared by all ligands. Let's go back to the top of the interface and see how changing some of these settings affects the variant list. Right now, you can see that the common pharmacophores we're attempting to find must match 5 out of the 5 ligands in our active set. Let's adjust that setting and see what happens. If we lower the setting from 5 to 2, you can see that the number of possible variants in the list increases from 22 to 40. In this case, the reason that the list of variants grew is because there are high feature frequencies that show up in at least 2 of the active compounds, but not all 5 of the active compounds. For example, if 2 of the 5 compounds contain 4 hydrophobic sites, the variant AHHHH appears in the list. That's 1 acceptor and 4 hydrophobic sites. But if any of our active compounds don't contain 4 hydrophobic sites, we'll never see that variant in the list if we set the must match setting to 5 out of 5. A pharmacophore that just matches 2 out of our 5 active set compounds probably isn't very good. So we'll change the setting back to normal, 5 out of 5, which will require common pharmacophores to match all of our active set compounds. And indeed, you can see that changing this setting causes the AHHHH variant to disappear from the list because some of our actives don't have enough hydrophobic sites to make this variant possible. Next, let's take a look at these 2 options near the top of the interface for maximum and minimum number of sites. These options control how many sites the common pharmacophores that you search for will actually have. In this example, we'll increase the maximum number of sites to 6. With the current maximum and minimum values of 6 and 5 respectively, this is telling Phase to first search for common 6-site pharmacophores, and then, if none are found, to go ahead and search for common 5-site pharmacophores. With this many variants in the list, though, it's unlikely that Phase will fail to find any common 6-site pharmacophores. Finally, let's take a look at the feature frequencies table. As the name implies, this is a table that you can use to specify how frequently you want certain features to appear in the pharmacophore model. In other words, this is where we could implement those hypothetical considerations I mentioned earlier, such as enforcing at least a single donor feature in the pharmacophore model. This is extremely easy to do, so let's go ahead and try it out. There's a column for minimum and maximum feature frequencies, and all we need to do is set the minimum property for H-bond donors to 1. Not surprisingly, the variant list is updated to remove any variants that don't have at least one donor feature. But not only does the variant list update to reflect the settings applied in the feature frequencies table, the feature frequencies table will also automatically update to reflect changes made to the settings it left. Take a look at what happens to the available and maximum column when we change the number of active ligands that the pharmacophore needs to match. As you can see, the available and maximum values change for donor and hydrophobic features. This is reflecting the same change that's also caused the variant list to broaden in scope, just as we saw before. Now, let's undo the last couple of changes and try something else. Okay, so things are now as they were when we first took a look at the feature frequencies table. What I want to do next is decrease the maximum values for a couple of features. This is because, in general, pharmacophores that have an overwhelming abundance of one feature type typically aren't especially good models. You'll note that the maximum column is initially set to the same value as available. The available property is automatically set according to the number of sites and must-match settings that we apply. For example, we can't have more than 4 acceptor features in a variant, so the available setting for acceptor is set to 4. By default, phase will look for a maximum of 4 acceptor features in the common pharmacophores that we're looking for. In this example, though, we'll decrement that number down to 3. Having already seen what happens when we've made these other changes up here, it's not surprising to see that the variant list is automatically updated to reflect these additional changes. In this case, we've pared it down a little bit, and we're ready to run the calculation. I'll do that by clicking on the Find button, and then clicking Start. I'm running this job on a single processor, although it's worth noting that you can distribute Find Common Pharmacophore jobs across multiple CPUs or cores if need be. Now the green icon in the upper right-hand corner indicates that the job is running, and you can click it at any time to view the log file as the calculation progresses. While our calculation runs, I want to take a moment to point out some advanced options that we haven't used yet. I'll click on the Options button here. These options allow you to set various parameters that have to do with the algorithm used to find common pharmacophores. Phase uses a novel, extremely efficient partitioning algorithm, the substance of which is a bit beyond the scope of this video, but suffice it to say that the options pertaining to this algorithm can be found here. I want to take a moment to note that the calculation shouldn't take especially long. If it seems like the calculation is taking far too long to run to completion, that can be a sign that you may have chosen too large or diverse a set of actives, that you may have a needlessly high number of conformations for your ligands, or some other problem. Once the finished job is incorporated back into the Maestro interface, you can see that the results table is populated. Each variant for which one or more matching common hypotheses were found is listed here, as well as the number of common pharmacophore hypotheses described by that variant. As you can see, it's not unusual for there to be multiple pharmacophore hypotheses that have the same feature counts. The difference between these multiple hypotheses is that even though they contain the same feature counts, those features are located and oriented differently with respect to one another. Now that we've found common pharmacophore hypotheses, in which particular arrangements of features are shared amongst our actives, we're ready to determine which of these hypotheses best describes the arrangement of features that confers ligand activity. In the next step, we'll attempt to do so by ranking these hypotheses using a scoring function.